Hi, my name is Wolf, and in the next few minutes I'd like to introduce you to the main ideas of our work, nonlinear dynamics of multi-agent reinforcement learning in partially observable environments. So what is the problem? Complex adaptive multi-agent systems are all around us, whether we think of animal swarms in biology, multi-agent systems in technology, or even social systems and public policy. Now, complex systems theory tends to focus on very simple individuals and interaction rules to explain some emergent collective behavior. On the other hand, fields such as machine learning and cognitive science usually focus on one single intelligent individual solving some task in a complex environment. Our work addresses the question of how can we combine these two approaches, and specifically we ask, how can we model the effects of changing and uncertain environments on the collective behavior emerging from individually self-learning agents? We built our work on top of the widely used temporal difference reinforcement learning algorithm in a multi-agent environment interface. Here, we have a couple of agents, each with their own set of actions, and an environment consisting of a set of states and rules for its dynamics. At each time step, each agent selects an action based on their current policy, and then the joint action exerts on the environment, which may change its state, and as a result, each agent receives a reward signal and observes the next state of the environment. However, here, this observation function may be an imperfect mapping from the true next states S prime to an observation O prime, which the agents then use again to choose their next actions. We can summarize these steps as the interaction part where, in essence, the agents try to assess their current temporal difference, also known as the reward prediction error in neuroscience, which tells the agents how to adapt, how to change their policies in order to receive more reward over time, which happens then in the adaptation phase. We use this framework because of its many ties to game theory, machine learning, neuroscience, as a dynamic, adaptive, and principled way to microfound the behavior of the agents as a result of the specific environment they are embedded in. In our paper, we aim to use dynamical systems theory as a mathematically elegant and efficient description in order to improve the understanding of the emerging effects of this collective learning process in changing environments. Related work did not focus on this aspect of the changing environment so far, which we saw is key for a principled and adaptive link to the resulting agent behavior. And specifically, in our paper, we improve on a general method from some of my previous work to the case of partially observable environments. So, with this method, we started from any standard stochastic, independent and model-free reinforcement learning algorithm, and then mathematically separated the timescales of interaction and adaptation in order to arrive at a set of deterministic, now capable to handle partial observability reinforcement learning equations, where the updated policy xt plus 1 equals the old policy xt times the exponent of the policy average temporal difference error multiplied by the learning rate and probably normalized. So, much like the ideal gas model in physics, you can understand these equations as an ideal model of the multi-agent reinforcement learning process. To illustrate this, I applied David Marr's famous concept of having different analysis levels for cognitive science, which recognizes that it is not only valid and fruitful, but even necessary to analyze cognition by forming abstraction barriers. Here we have the computational level, an abstract characterization of the computational problem that is being solved. And in our case, this would be game theoretic or social welfare solution concepts. We have the algorithmic level, consisting of the algorithm executing that solution, which in our case is multi-agent temporal difference reinforcement learning. And last, we have the implementation level, the hard or wetware implementing that algorithm, which we do not need here. Now, existing methods to study multi-agent systems, such as analytical game theoretic solution concepts and simulation-based learning algorithms, both have their advantages and disadvantages. The analytical tools offer an analytical understanding, often quite fast, but only because they do not scale to large problem sizes. And they are mostly always static concepts. Simulation-based learning algorithms, on the other hand, are scalable and dynamic, but also quite resource-intensive and often hard to interpret and to reproduce. So the idea is to embed the learning dynamics into this framework as an algorithmic level of high abstraction between the computational level and the algorithms of lower abstraction. Now, this exercise allows us to form precise connection between the levels. First, the learning dynamics form a boundedly rational account to game theoretic equilibria. And second, the learning dynamics resemble learning algorithms that have a very large, infinite memory batch in which the agents store experiences and replay them. Memory batch learning is a very common refinement in reinforcement learning. So here you see a policy trajectory, also in policy space, the dynamics in red, and multiple realizations of the algorithms in blue. And you can see that the dynamics match the algorithms quite well, even for moderately small batch sizes. So in summary, the learning dynamics represent a kind of memory mean field limit with a perfect model of the environment and the other agent's current policy, which offers an analytical understanding, being deterministically reproducible, computationally lightweight, and a principled account of dynamic agent behavior. And scalability is ensured by the connection to concrete process learning algorithms. Now, in the next two slides, I just want to highlight two example systems you can study with this very general method. First, we find that partial observability can stabilize an unpredictable, chaotic learning process. Here, you see the dynamics occurring in a two-state zero-sum competition with perfect observation. The learning is cyclic and partly chaotic. If now both agents are partially unsure in which state they are currently in, the learning appears already dampened until it quickly converges to an equilibrium reward of zero when both environmental states have become indistinguishable. Also, you can see here a phenomenon from dynamical systems theory. The learning dynamics have separated in a fast direction, circling into the top downward direction, which has become the slow direction. The second example concerns the critical problem of the emergence of cooperation. In our particular environment, the agents face either a prisoner's dilemma tragedy or a stack hunt coordination game with equal probability. But as in the previous example, they are unsure about the true nature of the game, adjustable by a noise level parameter. So when both agents are likewise unsure about the game they play, increasing the observational noise first decreases overall performance. However, at a critical level of observational noise, we see a sudden jump in rewards and the mutually high rewarding behavior becomes stable. In the bottom plot, we also observe the dynamical systems phenomenon of a critical slowing down of the learning process before the bifurcation point. So partial observability induces a critical transition towards cooperation. However, if only one agent is unsure about the true environmental state and the other agent remains perfectly knowledgeable, we observe that the knowledgeable agent exploits the unknowledgeable one. And interestingly here, by a different kind, a more smooth bifurcation, also at a slightly different critical noise level. I believe that investigating these connections between critical transitions and collective learning presents an interesting avenue for future work. But for now, let's conclude. We hope that the presented dynamics become a formal yet practical, lightweight, and robust tool for researchers in biology, social science, and machine learning to systematically investigate the effects of interacting, partially observant agents. If you have any questions or comments, please do reach out. And with that, I thank you very much for your attention.